Yeah, today I'm going to present the paper Encoder MI, membership inference against pre-trained encoders in contrastive learning. It is just published in this year's CCS from the Neil Gong's group from Duke University. Yeah, first, I will give an introduction about the contrastive learning. Contrastive learning is a machine learning techniques used to learn the general features of a data set without labels by teaching the model which data points are similar or different. Yeah, for example, even though no one tells us that there's a cat or dogs, we can still realize that the two cats look similar compared to the dog. By merely recognizing the similarities or the difference between our full reference, our brains can learn the high-level features of the object in our world. So for the contrastive learning, given amount of unlabeled data, such as the image or text, the contrastive learning aims to pre-train a neural network called the encoder that can be used as a feature extractor for many downstream tasks, such as we can enlarge this encoder into some downstream classifier that we can first use the encoder to generate the feature vectors of the input image and use this generated feature vectors for the following classify tasks, such as this. So in brief, the goal of the contrastive learning is to learn such an embedding space in which the similar samples pairs stay close to each other, while dissimilar ones are far apart. So that is the main idea of the contrastive learning. It is a kind of unsupervised learning. An essential part in the contrastive learning is the data augmentation. Given an input image, the data augmentation module will create another random input, here called the augmented input, by a sequence of random operations, such as the random grayscales or some random resized and each others, so that we can obtain some augmented data from the same original ones. We call this augmented data the positive data pairs. And then the augmented data from different original data, such as the image, we'll call them the negative input pairs.
One question, Jiadong. So what is the output of the contrastive learning? It's like the k-means or like the PCA, like the clustering algorithm. The output some groups of data is that the output of the contrastive learning.
And the input of the contrastive learning is the unlabeled data.
Yes.
And the output is an encoder.
Oh, it's an encoder.
Yeah, encoder. The output is the encoder. The input is unlabeled data.
And the output, I mean, then the encoder's output is the downstream classifier?
No, the encoder is the output of the contrastive learning.
Oh, yes. But here, you build like a pipeline, right?
The pipeline.
Eventually, you will use the encoder to be a part of the downstream classifier.
Yes.
Because you will generate some vectorized data.
Yes,
and you can measure the vectorized data's distance to decide so which data is like close to another one.
Yes.
It's like the word embedding.
Yes, it is an embedding.
Okay.
And then go on. So roughly speaking, the idea of contrastive learning is to pre-train an image encoder that it outputs similar feature vectors for two augmented inputs created from the same input, and outputs the dissimilar feature vectors for two augmented inputs created from the different input. So the contrastive learning formulates such similarities as contrastive laws, which for example, an image encoder is trained to minimize. So different contrastive learning algorithms will have different design of these loss functions, but they all share the same ideas. And then I'll talk about the motivation that how to do the contrastive learning membership inference. we can observe from the whole process of the contrastive learning that this algorithm try to pre-train an encoder that outputs very similar feature vectors from two augmented inputs that created from the same one. So that when this encoder is overfitted, to its pre-trained data set, the encoder may output more similar features vectors for the augmented input from the same one. So therefore, in this paper, the author designed this encoder MI tools to infer input to be a member of the target encoder training data set if this target encoder produce similar feature vectors for the augmented version of the original input. So the the overall pipeline of the membership inference attack is like this. In this paper, that attack is called the inferior. It is aimed to build a binary classifier called the inference classifier, which it can predict the member or non-member for the original input. For the original input, whether it is in the training data set for the target outcoder. So this membership, the membership inference task is based on the membership features. In this paper, they generated the features of an input is based on the similarity scores between the feature vectors of the input's augmented versions produced by this target encoder. So that in the attack process, we will have original data. It can be an image. Then we will produce some augmented versions of this data. We can input this data to the target encoder. That is the encoder we want to attack. Then these encoders will give us some feature vectors of this augmented data. Then we can calculate the similarity scores of these vectors and put them to our trained inference classifier. It will tell us whether it is in the training data set of this target encoder.
So what is the overfit part? So in your last slide, you show this like a step, like overfitted, right?
Yeah.
So what is the overfitted here?
It is yeah. If the target encoder is overfitted to its training data set, then maybe it will train the encoder in many iterations, so that the encoder can have really better performance, but it will leak some information that the trained encoder will give more similar feature vectors from the augmented input from the original data.
So why? So if the model, if the encoder, the target encoder, if it's not overfitted,
it will still produce the similar feature vectors.
Yes.
But it is overfitted. It will produce more similar. So it is the motivation of this paper.
Yeah. So my question is why, when the target encoder is overfitted, then it will, leak the information. But if it's not overfitted, it won't leak the information.
No, if it's not overfitted, it will still leak some information. And Dr. Wang, in the simulation result part, this paper will discuss these overfitted issues. It will show some in different iterations when we train the target encoders. How about the attack performance, and how about the encoder's prediction performance?
And how they justify the encoder is overfitted or not? Using like value change or convergence?
They do not talk about. They do not give the details about how it overfitted.
I'm not saying how it's overfitted. Is how we define the overfit, right?
Yeah.
For example, if you train a model like 1,000 times, 1,000 epochs, it's not overfitted. But if you like train it like 2,000 epochs, it might be overfitted, right? So how we can justify whether the model is overfitted or not here?
In this paper, they do not talk about details about this overfitted.
Okay.
Because overfit it is not whether this membership inference can be success do not determined by this overfitted, but overfitted encoder are more likely to be attacked.
I see. They're trying to use the overfitted encoder to motivate the idea.
Yeah.
The target encoder will leak information.
Yeah.
And particularly for overfitted encoder, they will leak a lot of information. That's why they can have the story like this, right?
Yes.
Okay.
Yes, and actually, based on my paper readings, most of the membership inference are all based on the motivation of such overfitting. That's our overfitted
information from the overfitting.
Yeah.
Okay.
Yes, overfitting the model will proven to generate many strong. It will produce some strong result based on the design ideas of this training algorithm. But it will the stronger of the result, the more data, more privacy data will be leaked.
Yeah, I saw some paper talking about how the model could be fitted into the data. And they are using like a feature information to describe how the model could be fit into the data. Then maybe we can use feature information to describe whether the model is overfitted and the level of overfitting.
Yes. Yeah.
Okay.
I think so. Probably so. Dr. Wang, probably I think so. You're asking so. What's the why the overfitting it can cause the similar feature vector, right? So I think this is because for the feature vector, the dimension space is fixed. So if you have more input, and then you will generate more feature, more feature vector, but the total dimension space is fixed. If you have more feature vector, definitely you will have more similarity.
I see.
Yeah, it's like that.
Okay.
Jiadong, I have a quick question. Just like you mentioned, right? So the membership inference attack really rely on the correlation between the original data and the output. You know, if you don't talk about the paper, you talk about the general membership inference attack, right? So you get some output, or you try to, you know, reconstruct the training data or whatever. It really rely on the correlation between the original input data and the output. I think the paper here is a little bit tricky here. They just change the output into the, I don't know, use the encoder to generate overfitted augmented data. If the augmented data is very similar to the original data, then we can launch membership inference attack, right? I mean, you got what I mean here, right? They just replace the output with this kind of augmented data. But the relationship still stay there, right? So that's what a membership inference attack rely on, right?
Yes.
So
After all the presentation, I just want to say that I'm a little bit disappointed after reading this paper. Because it's just like they use the old mechanism in a new learning story, just like this. But they all share the same attack idea.
Oh yeah, I'm sorry to disclose the secret at a very early stage, but I mean, that's very intuitive to think of as long as you know the fundamental things of the membership inference attack, right? So okay, thank you.
Yeah, if there's no questions, I will go details about how they build this.
Oh, by the way, for this one, do we need some ground truth data to do the similarity checking and train the membership inference classifier?
Yes, I will tell them in the next slide.
Okay, so Jiadong, here in this figure, so the original data and the right side, the training data, what's the relationship?
Oh, there's no relationship. Here, the train data is used to train this target encoder. we don't know in the real attack scenario, we don't know any about this training data. Here, the original data is the data we want to know that whether it is in the training data set.
Okay.
Here I use the original data is to differentiate from the augmented data versions. And then I will talk about how to build this membership inference classifier. The first step is to train a Jiadong encoder whose ground truth membership or non-membership relationships are known to the inferior. In particular, the inferior split the Jiadong dataset into two non-overlap subsets, the Jiadong member dataset and the non-member dataset. Then the inferior will pre-train a Jiadong encoder using this Jiadong member dataset. Here, to pre-train an encoder, it will depend on three key dimensions: the pre-trained dataset distributions, the encoder architectures, and the training algorithm. So in this paper, the authors categorizes inferior background knowledge into these three dimensions. And if the inferior have access to the target encoder's architecture, or he knows the training algorithm, he knows the pre-trained dataset distributions, you will use the same one, or use the data with the same distribution. And if the inferior don't know anything about the don't know about this knowledge, he will just use another. He will random pick architecture or algorithm for the contrastive learning. And also, I will talk about this. When I read the paper in this part, I'm quite looking forward to that, whether they will have some unique designs that, since they give this combination, they will have 8 combinations in these three dimensions, whether they will design 8 kind of algorithms to train the Jiadong encoders, but actually they do not do this. They just do some they just do some experiments in their simulation parts, and so they do not have the unique design when the inferior don't have the knowledge of each of them, or like this. They just mention this background knowledge in this part. So then, so next they will extracting the membership features. Given an input X, it is the original data. They will first create some augmented input data using some data augmentation module algorithm. This data augmentation module can be carried in the encoder training algorithms. And then they will use the Jiadong encoder, here the Jiadong encoder, to produce some feature vectors for each augmented input. And here in this paper, the membership encoder feature, the membership features of the original input consist of the set of pairwise similarity scores between the different feature vectors. Here, formally they use S to represent the similarities between two feature vectors. So in this paper, they omit the explicit dependency of the X of the these two augmented data, so that they just calculate the half of the similarity scores for all the combinations, and these similarity scores should tend to be large if the input X is a member of the Jiadong encoder. So since we have the membership features extracting algorithms, we can constructing an inference training data set. Giving a Jiadong member data set and a non-member data set, and the Jiadong encoder, they can construct an inference training data set, which used to build the final inference classifier. In particular, given the input X that belongs to this Jiadong member data set, they can extract its membership features, that the similarity scores, and assign the label 1 to it. Here, the label 1 represents the member. And similarly, for the data in the non-member dataset, they will also calculate the membership features and assign a label 0 to it to represent the non-member. So that based on these two dataset, we can construct the inference training dataset with the label.
So Jiadong, where are these two datasets? So where do they come from?
They are all come from the Jiadong dataset. If the inferior know the data distribution of the training dataset, they will use some dataset that have the same distribution. If they do not know this knowledge, they will random pick some data and split into two parts, the non-member and the member.
But what's the criteria to split these two parts? Because this is very important. If you already know the training set, why you need to infer this? If you don't do this, you said just randomly to pick up a dataset and split to this member dataset and non-member. But what's the criteria for this splitting?
They do not have some special criteria. They can just split this dataset into two non-overlapped parts.
Just randomly to split?
Yes.
So there's no special requirement for this dataset?
No. In my opinion, it is not a very important. It is not a important part, because the main idea that we want to generate this two member and non-member, that we want to know the exact label of the membership features extracting from the input in this data set. We just want to know that, okay, the data in the non-members, we have these similarity scores, and then we give them a 0 label, just like this. So for the member that so here the Jiadong member data set is used to training this Jiadong encoder. So we have their similarity scores and we want the label 1. That means that these similarity scores are trained to leak some image, leak some information, just like this. The split it is just a random split.
And Jiadong, what's the difference between non-member and member datasets?
Here the member dataset is used to train this Jiadong encoder. The non-member is just a dataset that do not involved in the training process of this Jiadong encoder.
So the data from the shadow dataset is from the original dataset, or is collected by the
collected by the inferior, just like this. The inferior collected some data set and split into two parts, the non-member and the member. The member we are used to train the Jiadong encoder.
Okay. But they don't have the access to the training dataset, right?
Yeah, they do. The training dataset of the target encoder, right? They don't know.
They just try to guess the membership of the.
Yeah, they don't know. And the only point here is that maybe they will know some data distribution of the training dataset, so that when they collected this dataset, they can collect some data have the same distribution, but they do not. But this Jiadong dataset is not overlapped with the training dataset.
The condition is they don't have direct access to the training dataset.
Yes.
Encoder, but they have the knowledge of the data distribution of the training dataset.
Yes, maybe they have this knowledge.
What kind of like a distribution, the label, the number of data samples under each label, or?
All of them are possible. It is based on the knowledge about the inferior.
Sorry, what do you mean by all of the what?
This distribution is not specified in this paper.
Okay.
They can know, yeah, this distribution can be some labels or some features. All of them are possible. If the inferior know this information, they can nitpick it some data set, so that their attack can be stronger.
Okay.
Hi, Jiadong, I got a question. What's the relationship of this shadow encoder and the target encoder?
Target encoder. There is no there's no relationships about this shadow encoder and the target encoder. We want to train this shadow encoder is that we want to use this shadow encoder to construct this training data set so that we can use this training data set to construct the classify.
But do you know the encoder architecture of the target encoder or not?
They can know the architecture and they can know the training algorithm.
So the only thing they need to determine is the corresponding parameter of that encoder, right?
Yes. They can know this knowledge, but they can, if they don't know, they will random pick feasible algorithm and feasible architecture.
But you need, in that case, probably you need more trials.
Yes. So based on these 3 dimensions, the knowledge of the target encoder, they will have 8 combinations.
So the goal here is not to simulate the target encoder. They just want to create some training data sample.
Yeah. Yes. Here the shadow encoder here is used to construct this training data set. That they want to know that they want to know if the data is not used to training this encoder. So what is the kind of the feature vector? What is the similarity scores of the feature vectors? And if the data is used to train such shadow encoder, so what is the characteristics of the similarity scores? And of course,
I'm sorry to interrupt. So if you don't know the architecture of the target encoder and you construct this this training process, and how can you really believe your decision bound, like here you got some score to you are regarded as from the same member or not, is exactly the same with this target encoder, because you have different architecture, you have no idea of their training data, and so you have no knowledge of this their embedding. So the score, the distance or the similarity between 2 points are decided by your own constructor or your own design. So how can you transfer this knowledge to that target encoder?
Yeah, I know. These are good questions. I also have this. I also have these questions when after I reading this paper. So the one reason I can think about it is, right now, the state of the art contrastive learning algorithm. There were only 3 popular algorithms, and they all share the very similar architecture and algorithm. The only difference between this popular constructive learning algorithm is how they choose the loss functions. That's the only difference about the loss functions. So although we have different architecture, we have different constructive learning algorithm, but they are quite similar. So that is
yeah, that's true.
Yeah.
Actually, recently I also read some papers related to this constructive learning, and the result is they have very similar loss function.
Yes.
Right. They
Yeah.
also use this NCE, right? And
Yeah.
but for different application, it seems they try to construct different positive samples and negative samples, or they try to use different architecture to be the encoder.
Yeah.
So here, yeah, I agree with you that they have very similar loss function, but it seems like they have very different encoder. So the latent space, the dimensional, the dimension of the latent space is quite different, and you can, arbitrarily choose one, dimension, and they say this is the best representation, and then they use some downstream task to validate their design. So I'm very doubtful about this transfer, the self-designed.
I agree with you, actually. I agree with you. I also have these questions. So I still have a little doubt about the results because yeah. So in the result part, if they do the experiment that we don't know any about the data distribution, and we don't know the encoder architecture, we don't know the training algorithm, but they can still have the accuracy of more than 80%. So, but however, it is published in CCS, but I agree with you. I have some doubt about the design.
Thank you.
So I have one more question. So based on my understanding, if the original data, that original data is the crafted data, right?
Yes.
Okay. If this original data is large enough, they will always have the high performance because this crafted data properly include already contain the part of or some of the training data.
Yes.
So they can always get the high performance, right?
Yes.
But have they conduct experiment to explicitly to say that the original data, it's not belong to the training data. There's no overlap.
Yes. Yes. In the experiment, for example, they use the CIFAR10 dataset. They will split it into, first they will split it into two parts, one for training the target encoder, and another one with used to training the shadow encoder. They will not overlap.
But how can you guarantee that these two parts there's no overlap? Probably there are some parts there are still a lot of similarity.
Yeah, they follow the same distribution, right? So
yeah, they follow the same
yeah.
distribution. And and in the experiment, if they want to have the different distribution, they will use the data set in the CIFAR10 to train the target encoder and use data in the, for example, in the ImageNet to train the shadow encoder.
Okay, so they still required to have the similar distribution. How about if the data distribution are totally different? So what's their performance?
Still good. Their performance is still good. And when they do not know the distribution, they will use data in different data set. And as they will use the data set in the CIFAR10 to training the target encoder. And they will use the data in the ImageNet to training the shadow encoder. And they announced that the data in the ImageNet and the data in the CIFAR10 will not share the same distribution.
That's interesting. So what's the target encoder? Which algorithm they are using?
In the experiment, they use two popular algorithm called the MOCO and Phillips. They are the two popular and state-of-the-art contrastive learning algorithm.
And for this shadow encoder, so which algorithm are using?
If the inferior know the knowledge about the algorithms, they will use the same one. If the inferior don't know this knowledge, they will use the different one.
Okay.
Jiadong, I think this may be a little trick because from in machine learning, if a classifier trained by ImageNet can generalize well to CFA10, because ImageNet is much compressed than CFA10.
Yes, but they may not share the same distribution.
Yeah, but as you mentioned, the target mode they trained as CFA10, but when they train a shadow encoder, they use the ImageNet. What about you change the two data sets, use the ImageNet to train a target mode, but use the CFA10 to train a shadow encoder. I think the result were much different. So I think maybe use this trick because a common practice to pre-train CFA10 dataset is use a pre-trained ImageNet, so that a pre-trained net can generalize to the CFA10. This is a kind of transfer learning.
Yeah, they have 3 experiments, and
Yeah.
the situation you mentioned, they also do the experiment. Yeah.
How about this, Jiadong? You train the target encoder, use something like, I don't know, any kind of image data set, CFR10, ImageNet, but you train the shadow encoder, use some audio data set. Do they try this?
No.
I
believe in this
don't think
case-
it works.
Yeah, it's not going to work. I mean, for this concept, what do you call it? Contrastive learning or whatever. I think, I don't know, probably in general, all the image, how certain kind of features can be extracted according to contrastive learning. Probably, it doesn't matter what kind of data set, what kind of distribution. It's really, I mean, depends on the, I don't know, probably the image feature, image itself. Probably we give a different data, the audio data or some other data.
Yes.
It's not going to work or something. I don't know, but I guess, yeah.
Well, in the experiment part, they always have some tricky part.
And also for the black box, like if they don't know the algorithm for the target encoder, so what's the algorithm they're using for the shadow encoder?
They will use another popular
Which one?
contrastive learning.
Okay, yeah, that's should be an issue. How if for this black box, how can they know it will be contrastive learning? So why they can select this one?
They target to the contrastive learning so that
But in the real world, you don't know whether the contrastive learning is used or not. If we use, okay, I think so now I got the tricky because they are contrastive learning. So they use another contrastive learning that definitely can simulate some and also have high similarity.
Yes.
Yeah, I think we have ever done this experiment. So Yihe, you are here, right?
Yes, I'm here.
Yeah, I think you have ever done a lot of this experiment, right? If, for example, if your Black's model is the neural network, so and then you use another neural network, even different layer, different structure, but you can still get the very high similarity, right?
Yeah. They have the high correlation between the data points.
Okay. Yeah, in this case, I think this paper, I don't know how it can be, how can it go to the CCS? So this is a strong assumption. So it's impossible to know whether the contrastive learning is used or not. So how can they can they build the model to use the contrastive learning? This is a key design step.
So in some cases, there are some. So yeah, there are some real cases use this learning, like handwriting verification. So we can assume that this system use the constructive learning, and maybe they can try to attack this model.
Yes, and in some machine learning as a service platforms, they will publicly announce that they will use what kind of learning method they use to build this API. So maybe.
Okay, so if they announce this, so it makes sense.
Yeah. So yeah, all of you are interested in the experimental setup. So that is a setup. Yeah, if they know the data distribution, they will use 100 image from the same one. And if they don't know, they will use a different data set. And if they know the architectures, they will use the same one as the target node, use this architecture. If they don't have this knowledge, they will use the VGG11. And also for the algorithm, the target is use the Moco version 1. And if they don't know, they will use the SimClear. But actually, I'm not an expert in the contrastive learning. I don't know whether these architectures and these algorithms are share the high similarities so that they can achieve the quite good performance.
So here the ResNet and VGG is used for the shadow encoder, right? When they don't know the target encoder, right?
Yeah, if they know the target encoder, they will use the same one, the ResNet. If they don't know, they will use the VGG11. Yeah, here the target encoder will always use the ResNet.
Okay.
Here, do they need to know the dimension of the feature, the representation feature, the dimension the dimension
of the input data set?
No, not the input, is the output representation feature.
Or the
embedding,
the
embedding feature.
vector.
Sorry, the dimension of the output.
Yeah.
I think he want to ask the size of the feature vector.
Yeah.
We do not mention it in the setup.
So it means even they don't know the target encoders architecture, they can design an encoder with the dissimilar dimension of the feature. And I got you. I see. It's the same question as what I asked before.
They don't mention about the dimension of the output.
Why I ask this question is because from my readings, they most focus on the downstream tasks. So the representation feature is kind of critical. The feature, the encoder can be arbitrarily constructed, but the representation feature is very critical because it will be used for the downstream tasks. So here, I want to know why do they need this knowledge of this representation feature at least?
It seems that they do not need to know this knowledge. So the output, the dimension of the output of the representations, it is whether it is result from the encoder. It is whether if this knowledge will not used to construct the encoder, maybe we do not need this knowledge when we try to construct the shadow encoder. And based on Yeah, and it seems that the dimension of this output is the result of the encoder. So maybe they do not need this knowledge when they just construct the encoder. And they do not care about the downstream tasks. They just want to know whether they can inference the encoder, just the encoder, not the downstream classifier.
Yeah, because they need to calculate this similarity score between two points.
Yes.
So actually, it's the same question as I asked before. I don't know whether this latent space, the dimension of the latent space is critical for this similarity calculation. I don't know. So I asked. Yeah.
Yeah. So when they calculate the similarity, they use different similarity matrix, and they do not mention some details about this one. They just say they use some sign or others to calculate this. Yep.
Thank you.
I will go back to the last part, how to build the inference classifier based on the inference training dataset. And in this part, they also provide three types of classifier. The vector for the vector base, they will rank the similarity scores in the scores in this set and in the descending orders, and created a vector based on the similarity scores as an input to train the classifier. And the next for the set base, the classifier will take the similarity score set as an input and do not do any ranking operations and predict the label for this set. And for the threshold based, it is a little bit different from these two, and they use the average similarity scores in this set or as an input to infer the membership. And in particular, how to define this threshold is very important. So here, given a threshold theta, they use the alpha theta to denote the number of inputs in the member dataset. A member dataset whose average similarity scores is smaller than the theta, and they use the beta theta to denote the number of inputs in the non-member dataset whose average similarity scores is bigger than the theta. So they want to minimize this matrix, that they want more similarity scores larger than the theta if they belongs to the membership dataset, and more similarity scores smaller than the theta if it belongs to the non-member dataset. And for this threshold based classifier, they do not need the machine learning training. They can just calculate this theta, and then when they do the attack, they input similarity scores. They can just compare this similarity scores with this theta to determine whether it is in the training data set. So recall that this is the attack process of their membership inference attack. So they will train this all the process in the previous slides are used to train this inference classifier. And then in the real attack, when we got original data, we will create some augmented data versions and input them to the target encoder, and then they calculate the similarity scores of the feature vectors, and based on the different types of membership inference classifier they built, they will manipulate these similarity scores in three different types. and input them to this classify, and it will return the result of whether this data is in the trained data set of the target encoder. Then, at last, they do the evaluations. For the experimental setup, they use 3 datasets: the CIFAR10, STL10, and TNA ImageNet. They are all the image dataset. And they training the target encoder, that the encoder they want to attack, use the RESTnet architecture and the MOCO algorithm. It is the state of the art and somehow popular contrastive learning method. And when they training the Jiadong dataset based on whether they have these 3 knowledge, they will use different strategies. And they will all choose the 20 image from the same or different dataset and split this 100 image into equally split into they will split this data this 200 image into 2 100 image for the member and the non-member. And when they building the inference classify, they training the vector-based encoder encoder classifier use a fully connected network with 2 hidden layers. And when they use choose the set-based encoder classifier, they use the deep set algorithm to do the set-based classifier. And as I mentioned, when they use a threshold classifier, they do not need any machine learning based training. They can just calculate the best. They can just based on statistic calculations, they can know whether they can know the optimal threshold values and just compare the input similarity scores with this threshold. And they use the accuracy, precision, and recall as the 3 metrics. It is these do not have some special designs in these 3 metrics, just the original definitions. And for comparisons, first they use 5 methods to infer the membership of a classifier, since they claim that they are the first one to do the membership inference for the encoder. So there's no counterpart. So they just use method for the classifier. And then of course, yeah, for these 5 comparison algorithm, they achieves lower accuracy, precision, and recall. And since they are not designed to infer the membership of encoder, they are just designed for the classifier. So the confidential score vectors can capture whether the classifier is overfitted for the input, but it cannot capture whether the encoder is overfitted. And then they do the experiment based on these 8 combinations according to the knowledge, and calculated the accuracy, precision, recall for their 3 classifier design. And I just show 1 table here, and they have 3 tables for the CIFAR10, TNA ImageNet, and the other image dataset. But all of them share the same trend. They all have a very good performance, even when the inferior don't know anything about don't know any knowledge about the contrastive learning and the data distribution. They can still achieve the performance over the 80%. And it is quite, yeah, I don't know why they have such good performance. Yeah, and they also discuss about these tables, that among these 3 dimensions of background knowledge, the training algorithm is the most informative ones. And there's no clear winner among the encoder architecture and the pre-trained data distributions. And besides, they also discuss about the impact of the augmentation and the similarity matrix. We can see from this figure that here the with the increase of the augmented input, the vector-based and the threshold-based classifier achieves better performance, but for the set-based encoder classified will get worse after a threshold. The author explain that the reason is when the augmented input increase, the number of pairs-wise similarity scores in the membership features increase proportionally, because each two pair of them will have a similarity scores, and then making the set-based classification harder. But why the set-based classification becomes harder? They do not give the explanation in details. And this table shows the impact of the similarity matrix. And from these tables, we know the author mentioned that the cosine calculation is the best one. The reason is that cosine similarity matrix is also used in the pre-training of the target encoder. That means that the popular contrastive learning algorithm use the cosine to train the similarity scores. So use the cosine to calculate the similarity scores. It can achieve the best performance. Actually, it is a trivial result. And at last, they also observed that the accuracy of the proposed method increased as the pre-trained data set becomes smaller. The reason is that the target encoder is more overfitted when the pre-trained data set becomes smaller. And besides, their methods are also less sensitive to the Jiadong data set size. The author do not give the explanation about this this observation. And finally, the Dr. Wang mentioned it as the first. They discussed how to do the countermeasures. They mentioned the preventing the overfitting by some early stopping. They give these two results. The first, the figure A shows the average pairs-wise cosine similarity scores for members and non-members of the target encoder as a member of the pre-trained epoch increase. They can observe that the average similarity increase for the member and decrease for the non-member as the number of the epoch increase. In other words, the target encoder is more overfitted and its pre-training data set more overfitted to the pre-training data set when they pre-train it with more epochs. And here the figure B shows the membership inference accuracy and of their proposed classifier and the classification accuracy of the original encoders So they can show that here they mentioned that the 80 epochs under the experimental setup is a better trade-off point, such that the original encoder can also achieve some better performance, while the membership inference accuracy is relatively low. So based on this figure, they think that they can use some early stopping to prevent the membership inference, while do not deteriorate the performance of the encoder.
For the figure A, the y-axis, the average cosine similarity, it is the similarity between what?
Between the augmented input of the same original input.
So between the original images and the augmented images.
No, between different augmented image.
Okay.
So is this two figures kind of a statistical one, or is it based on one specific experiment?
Yes. They just gave a case.
Just one case, right?
Yeah,
it's
just
not
one case.
Okay, generalized one. Okay.
They leave this part in the discussion part to discuss about the countermeasures. So they just say that the early stopping can help to preventing the membership inference to some extent based on this trade-off figures. And also they have mentioned the pre-training with differential privacy and adversary learnings, but they just mention it. But how to actually do the differential privacy and adversary learning to prevent the membership inference, they just leave this part in their feature book. Oh, sorry. Yeah, that's all of this CTS papers.
Okay, so any more questions?
So I stopped the recording.
Yeah, you can stop recording.